right, good morning. Good morning, Vincent and Bing Chen. All right. Yeah, so let's check out the announcements today. And good morning to you, to Brian. So other than the links to the YouTube live stream and the Google Meet session, there's nothing more today. Okay, so Holly can go ahead and get into the topics today. So we're still in section 2.1 of chapter 2. So that's the opening section. So you can see that Polly is trying to overview you guys how one design an application and implement the application. All right. So yesterday you hear about that at the beginning. You want to come up with the architecture of your app. So that includes, hey, defining what the components are, and the role of these components, functions of these components, and how they connect. And once you use socket to connect, you can start sending messages. Okay, good. Now, there's one slight thing that we have not yet talked about the socket is, hey, to define a socket, you need to say what transport layer service you want to use. And of course, there are some other parameters such as port number. Now, so we'll come back to talk about the first thing, what transport layer service we use to send the messages for your data. Okay, good. And before we can talk about the transport layer services you want to use for the application, we need to understand this thing called QoS, quality of service. Okay, there are generally 3 plus 1 QoS. And these QoS are QoS requirements. They are to describe what the user expectations are or the user demands are for your service, for your app. Okay. And so later when we talk about the transport layer services, those will be what? The options you can use to implement. So those are the supplies. So in a way, today, QoS is like the user demand. Transport layer service options, those are like the supply. And you as an app designer, you are kind of like a middleman in trying to connect the demand to the supply. Okay? So quiz A is exactly for you to exercise, playing the role of the middleman when you're designing, connecting the user expectation and the service supply. Okay, good. So here's the first video talking generally about the 4 QoS requirements. Now, in order to know what is the right transport layer service for an application, we need to think a little bit more about the application we are designing. What is the nature of the content we're sending, and what the users might be expecting. The first criteria is called the data integrity. This concerns whether the data needs to arrive without any loss. The key word here is that if the apps are about sending text-based content, for example, a file, for example, a web page, for example, a text message, then users are expecting 100% reliability. If we're sending audio video, it's okay to have some loss. Think about speaking a sentence. If we miss a syllabus here or there, the listeners being human beings, we are intelligent. We can still make up the full sentences or make up for what the speakers want to say by looking at the context before and after the sentence. Second criteria, growingly important, timing. This is especially the case for interactive applications. So the key word here is interactive. Internet calls, live video sessions, or shooting games, interactive games. Users are indeed expecting low delay. Okay, and you guys know. Third is throughput. Okay, this is sometimes referred to as bandwidth requirement. Nowadays, we send multimedia content, audio, video. Text-based content, it does not require too many bits to send them, so it's not an issue. But for video and audio, we do need a substantial amount of bits per second in order to deliver them, so that the bits after recovery, okay, is in good quality. So if you compare video versus audio, the throughput requirement for video is higher and audio lower. Text, much lower. So we need to somehow guarantee a minimum amount of bandwidth in order for these audio-video communication to be effective. text-based applications are elastic apps because there's no strict bandwidth requirement. The requirement is elastic. Fourth criteria, security. This is probably nowadays the most important criteria. Are the users expecting we are sending data such that we are protecting their privacy? Okay. So these four criteria together, we actually give it a special term. They are also called the quality of service. So before we can define what transport layer protocol we use, we need to think through what kind of quality we will be providing the application service. All right, so that is the theory. We have four kinds of quality of service. They will sound a little bit abstract. So when you're learning something, you start by listening to the theory. And the second thing we do is we exercise and give you a few examples. So next video is to share with you, given some of these popular applications we are already using on the internet, what are the QoS requirements people see? Okay, so check this out. Sometimes you'll find that after when you're learning something, listening to the theory, it'll be straightforward, but you still won't be able to exercise the theory until you look into the examples. Let's go over a few common applications and see if we could sort out their quality of service requirements, or in short, QoS requirements. First application, file transfer. Transferring files are static objects, most of them text-based. Therefore, in terms of data integrity, we demand 100% reliability. File transfers, we do not expect they arrive in a few seconds. Okay, so it's not delay sensitive. As a result, there's no strict bandwidth requirement. Therefore, the throughput part of the QoS, elastic. You can probably imagine email and web objects. These are transferring also files, email files, transferring web pages, okay, web page files. Therefore, the QoS requirements very similar. The second application here is real-time audio video. So, first of all, the nature of content, audio video, different from text. Therefore, keyword, non-text, it can be delay tolerant. Okay. Another is it's real-time, that means it's interactive. That's another keyword, which means we do have delay requirement. And for real time, that's showing the audio, video that's happening right now. So the delay needs to be less than hundreds of milliseconds. So you feel like it's happening right now. Audio, video, now there's time sensitivity. Therefore, we need to maintain minimum bandwidth. So there's a bandwidth requirement. And the requirement for audio, lower, video, higher. These days, some users might actually expect even higher bandwidth for video. Now, can you think and push a little bit and see if you know the QoS requirement for stored audio video? Well, first of all, keyword, audio, video, non-text. Therefore, you can probably guess data loss here is loss tolerant. What about the delay requirement for stored audio video? It should still be some requirement, but probably not as strict as the real-time audio video. And you're right. Delay can be a little bit longer. But given that there's delay requirement, the throughput is still hard. We still need to make sure that there's a minimum amount of bandwidth available. And audio, video, the bandwidth requirements are because of the nature of the content. So it will be the same. Audio, 5 kilobits per second to a megabits per second. Video, 10 kilobits per second to 5 megabits per second. Now what about this one? Yeah, interactive. The keyword is similar to the real-time nature of this application, isn't it? Except that this is now game data. So you can imagine, delay requirement here, just as strict as real-time audio video. Is it loss tolerant? It's a little bit tricky, isn't it? What about throughput? If there's delay requirement, then there's usually a throughput requirement, but it should not be as high as video or even audio. So here, just a few kilobits per second. Game, this part is debatable. For some games, for example, shooting game, some of the players would argue, I want no packet loss. Okay. But for most of the interactive games, it's okay to have some loss. Okay. And then the users, the players, can try to repeat actions to make it up. What about text messaging? Keyword text, so no loss. obviously. Throughput? Yeah, it depends a little bit on the delay sensitivity, isn't it? And text messaging these days, yeah, it's also debatable whether it's time sensitive. Some will say yes, some will say no. Okay. But you see also that the delay we experience in text messaging, most of them are probably thinking delay, not network delay. Okay. All right, so from these examples, you can probably sense that the traditional applications, the QoS requirements are quite clear. But the newer ones, like games, like text messaging, things get a little bit complicated. Right? You know what? You're right. Depending on the applications you're designing, depending your target audience, the QoS requirements might be a range. A lot of times you can satisfy maybe 80-90% of the users, but might not be 100%. Okay. All right, now let's check out the supplies, okay, the two options, two protocols that we can use from the transport layer. In order to find out what is the right transport layer protocol for an application, we also need to know what the options are. We do have two, TCP and UDP. TCP is the one more elaborated. UDP is very primitive. Let's focus on TCP here. The reason it's more elaborated is because it provides reliable transport. Think, a sending process and the receiving process. If we connect the two of them using a TCP at transport layer, data will always come to the receiver 100% correct. There's not going to be error. There's not going to be lost packets. How do we do that? Well, let's talk about that in Chapter 3. In fact, that's the main content in Chapter 3. For now, keep in mind, TCP provides reliable transport, no data loss. Second, TCP also does flow control between sending process and receiving process. The sending process here is checking whether the receiving process is busy or not. In case it's busy, the buffer gets full because data comes to the receiver and gets buffered temporarily here. If the receiving process is a little bit busy, the speed that we extract the data out to the application could be slow, so buffer builds up. If the sending process is sending data too fast, those data arriving to a full queue, full buffer, data get lost. If TCP is doing all it can to try to recover from loss, it doesn't make sense that sending process is sending data too fast to create data loss. So flow control, some sort of communication going on between the receiving process and the sending process so that the sending process will slow down. Congestion control. It's a little bit similar to flow control, but it's between all these other routers in the middle of the path from the sending process to the receiving process. In case any of the buffers, okay, in the middle on the internet is close to full, sending process slows down. If the buffer is no longer full, packets can go smoothly, speed also comes back up. Okay, so that is called congestion control in TCP. This, in fact, is also one of the main content that we'll talk about in Chapter 3. So for now, just keep in mind, TCP does reliable transport, flow control, congestion control. TCP, however, does not do this. Timing guarantee, minimum throughput guarantee, security guarantee. So the other three QoS requirements we talked about, TCP does not provide. The only QoS guarantee it provides is reliable transport. So this is TCP. Now there's one more feature about TCP. It's called connection oriented. To set up a TCP connection at the transport layer, the sender and receiving process also do some sort of control message exchange to set up a connection. So this part of internet, although it's a packet switching network, but the behavior is a little bit like the circuit switch network. And there's a reason for it. Okay? This is so that we have more communication so we could recover from errors. UDP, it does not do reliable data transfer. There's nothing really going, no more communication between the sending process and the receiving process. Sending process is send, receiving process is receive. It does not provide flow control, congestion control, none of these timing, throughput, security guarantee either. There's no connection set up. So this is really the native packet switching network transport layer service model. Now you know, TCP essentially does nothing. You're right. The question is, why do we bother having UDP? Why don't we just use TCP? Yes, if you recall, among all these applications we've mentioned, text-based content, we prefer reliable transport. But is there other kind of content that reliability is not necessary? It's okay to have some loss. Yes. Sending audio video is not necessary to have 100% reliability. So quite a few of these audio video multimedia services, multimedia applications, prefer using UDP as the transport layer service. Yeah, so after listening to this video, you know that, oh, TCP guarantees reliability. But in terms of throughput and delay perspective, not very good. UDP does not do any of the reliability thing, but relatively speaking, right, delay is shorter because there's no message back and forth between the receiving sending process. And by the way, in the video, when I say receiving sending process, I actually meant at the transport layer, okay, not the application layer, all right? But hey, guys, if it's still fuzzy, no worries. Next video, Polly shows you a number of these applications we're using on the internet and how the designers of these apps chooses to use TCP or UDP. So, examples. Here, let's go over some common applications and see what transport layer protocol they pick. Email. Well, in fact, remote terminal access, remote logging, such as the terminal you're using to remote logging SSH to the PA server. Web downloads, file transfer. All these are what? Text-based, static objects. Reliability important, but it's elastic, no delay requirement. So, not surprising, you see them all using TCP. So these are just the specific protocol, okay? Each of the application is using. Email is the application. The application layer protocol is called SMTP, Simple Mail Transport Protocol. For World Wide Web, this is the application. The protocol supporting World Wide Web is HTTP. File transfer, the protocol, FTP, standing for File Transfer Protocol. Now, these two other applications, streaming multimedia such as Netflix or YouTube Live, audio, video, reliability is no longer required. Therefore, you see, some streaming multimedia applications use UDP, but some stick to TCP. Internet telephony, Google Meet that we're using also on the side is one such internet telephony application. It's audio, video as well. So UDP, and sometimes some of these internet call services are TCP. And that takes us to quiz 8. All right, so let me switch to the whiteboard mode so that you can, see, okay, Polly's marks. So this is quiz 8. We do have 3 games, Farmville, PUBG, and RO, 3 games that I need you to ponder. Okay, so think that you are the designer, the implementer of these 3 games, and you are asked, okay, whether to use TCP or UDP to transmit the game data. Okay, so for each of the game, pick one, TCP or UDP, and tell why. So maybe I can explain a little bit more about, first of all, Farmville. So it's a web page based game to begin with. So it's a little bit more relaxed because the players will need to plant seeds for their crops, for their flowers, and they will need to wait for the real time to elapse for a while, and then they see the crops grow or the flower blossom. What's interesting about this game is that you can also visit your players can also visit players' friends' farms or garden, okay, and take some flowers they like as well and planting their own garden. Okay, so that is Farmville. Slower pace, okay, and just growing the crops. PUBG, okay, in the middle here, as you can see, okay, so this guy here is, nervous and looking for targets to shoot. This is a first-person shooting game, and when you're playing such a game, you are, constrained with the time, and you can only move within a certain area. So the gameplay is that the players will need to kill each other until the last one standing. Okay, super high pressure. Okay, everyone wants to be the one surviving in the end. Okay, and so how you survive depends on how fast you can localize your target and shoot. Okay, in precision. All right, so higher attention, faster pace. That is the kind of game PUBG is. Now, RO is a massive multiplayer online game. It's a kind of game that there are usually a lot of players. Okay, there's no time constraint except that when you guys are working in a team and battling a gigantic monster where you're looking to loot rare treasures or Uber equipment. Okay, so in this massive multiplayer online games, you have rich gameplay. It can be as intensive as PUBG, but part of the game could be like Farmville, because in RO you can also trade these Uber equipment or rare treasures in a market. So shopping in a market or negotiating over a chat channel with other players, that is kind of like Farmville. So RO, a mixture of different gameplays. How would you implement that game? Do you use TCP or UDP or both? All right. Now go to W4, quiz 8. Find your teammate. This is one of those open-ended quiz. Discuss. And you guys get 10 minutes to think and discuss. After that, come to the Discord channel, post your solution. And let's go. guys. So I see that some of the teams have decided earlier, faster than the others. But you know what? Those who are still arguing, the teams that are still arguing with each other, feel free. You still have time. Okay. But let me try to walk through some of the answers. The faster teams. Okay. Faster in terms of converging to a solution have already posted. So team 1 here says Farmville. It's better that we use TCP. Excuse my phone. Okay, allow me just 1 second, otherwise it's gonna ring forever. Oh, shoot. How do I turn this off? There we go. All right. Okay. Yeah, so for PUBG, UDP, because it's fast-paced, latency is absolutely critical in the shooting games. In particular, the player's time and game state need to be synchronized. Okay, because it's either you die or I die, isn't it? I can totally agree with the design here. UDP is a better option for PUBG. RO, for this mixed type of game, hybrid game, TCP. As battling the monsters in RO is probably not that critical in terms of delay. Okay, so the gameplay experience will not be too negative. Okay, negatively degraded. Okay, by delays. Here's a question from Peter. If UDP is faster, how come the slide still says it doesn't provide timing? Okay, very good point, Peter. You see, it's faster, but it does not guarantee that the delay is going to be fixed or within a certain bound. But you see that in PUBG, it is better that within the reaction time, reflex time. So it would be better if it's within 200 milliseconds. But UDP, it does not do anything, which means it actually does not guarantee that the delay is going to be within 200 milliseconds either. Okay, so it's better than TCP, but it still does not guarantee anything. Okay, all right. I hope that I explained the point on the side. Okay, very good. Very brave to take a stand. Okay, fast. So this is team 1. And guys, you know, for these open-ended quiz problems, feel free to take a stand and try to argue. But argument is not like, you know, you talk louder than you are successful at arguing. As you see on the streets commonly, in Oriental culture sometimes, arguing is that you say it with reasons, with rations, and better yet, being calm when you're saying it. Okay, so that's called being convincing instead of, you know, troublesome or scary. All right, so let's see the second answer here from team 6. TCP, because data integrity is a lot more important for Farmville than delay. UDP, as we see that streaming services also use UDP as that time is more important. TCP when collect some important goods. UDP when fighting the boss. Okay, so team 6 says, how about using both protocols? And we actually start 2 different sockets when we are trading very valuable, rare items, TCP. Hey, you don't want to have loss there, right? So use that TCP socket for trading. And when it's fighting, right, issuing comments to the server saying that you are, you know, applying a spell, that can probably be UDP as long as you go faster into the server. Okay, so fighting boss, maybe UDP. Okay, so use the UDP socket. Very good. Yeah, you paid attention in the video, obviously. I understand that many of you are paying attention. But you see, you can actually start 2 sockets within one app. If you started working on the PAs and PAs further down, you will see that you can actually, the team who already completed PA6 knows that you can have concurrent sockets going. Then of course, within a program, within an application, you could have different types of sockets, okay, for different types of data that you're sending. Team 11 says TCP for Farmville. Delay not very important. You know what, Stephen? Yes, someone completed PA6 already. And couldn't stop. Yeah, so that team, that someone, definitely a coder. Definitely a coder. All right. Steven? Maybe you are less, but hey, you know what, guys? Interest is something that you can also grow. Okay? But usually that requires also some patience. I don't know if you guys have this experience that when you met someone, you don't like him or her at the beginning. But hey, because you're in the same class, you can stay away from the guy. But after a while, you grow to like a person. Yeah, so think again. Maybe you don't like a specific subject at the first place, but if you stay patient, you might find that, hey, this is not so bad at all, and I can live with that. And you grow to like it eventually. I don't know if you like it. I mean, I was forced by my parents to take all these instruments lessons, like pianos, flutes, all kinds of musical instruments. I hated when I was young, but I love them now. Hey, don't take Polly's words from it. But I'm just, sharing my experience. Okay, you might have other experience, but might not be with the instruments, but with something else. PUBG UDP. Delay is very important. So I see in Team 11, Ethan, you guys have come up with a principle for you guys to decide what socket to use, isn't it? Delay. If delay is required, UDP. If delay is not required, TCP. Because I see also here, when you are designing RO, you thought that you want to use both kinds of sockets. Okay. If it's phi, right? Delay more important than use UDP. If it's just, trading or chatting, TCP. Delay, not a requirement. Okay, so you guys are making a decision based on checking whether delay is important. That is very clear, straightforward, and yet effective. And some of the teams look at both QoS, delay, and reliability. But I guess in terms of game, what's really, really critical will be like a PUBG kind of game. Delay, absolutely, absolutely critical. Reliability, is it really critical? Well, you see, trading goods, reliability, very critical. Okay. But I think the general rule of thumb is that if there's no delay requirement, you just, use UDP. It guarantees at least reliability. So that's, I guess, the kind of thinking in Team 11, right? Hey, interesting and not bad at all. All right. So even though you guys' solution look kind of similar, but you can see from how you argue for it and see the thoughts, okay, behind the team and what they find, the flow of the thoughts. And those are very interesting things to see, isn't it? Because that provides also perspective. So next time when you run into problems that you seem to, need to scratch your head and think, oh, I am in a dilemma. Then learn from these learn from your classmates' perspectives. Some of the teams like to simplify things, and it can be effective too. Let's see Team 2. Okay, Farmville, TCP. Doesn't require quick response. Yeah. Is it okay to use UDP for Farmville? I guess in your answer, you are implying that if delay is not required, just give it TCP and it ensures data reliability. It's better than UDP in this case. PUBG, definitely, absolutely. You want to make sure the delay is as short as possible. You probably want to make sure that the delay is constant among all players. Okay, that is actually what the first-person shooting game demands. It is very delay sensitive, but the kind of delay you want to guarantee is that it's constant among all players, so that it will be your reflexive deciding whether you live or die. Okay. ROTCP, much like Farmville, even if it's a major boss battling, because there are so many players, right? And so as long as the team composed, all of the characters are strong enough, you will eventually win, even though there's a little bit of delay. Interesting. Okay. All right. And guys, we should be moving on. So I would definitely walk through each one of users' solution and provide comments when I see interesting ones. So let's move on. Switch gear back. All right. So settled. Yeah. So quiz A. Just to summarize that the demands, user demands, and the supplies, how you can work. You see, you're demonstrating it already, right? You guys can discuss and come up with solutions yourself. All right. It might not be perfect, but as you start operating the game, you will receive feedback from your users, and you will learn also. Oh, maybe I want to change from UDP to back to TCP, or yeah, you see. Okay, so design is also oftentimes in running in cycles. Okay, but you will have to be brave and take a stand to begin the business at the first place. And so if you fail in a business, I understand that it's very costly, financially and mentally, but be strong, be brave, be courageous. Okay, come back. Okay, give yourself another opportunity. All right. But if you realize that you probably are not as thoughtful as the people who really run businesses successfully, you want to observe more before you start again. Okay? All right, so the switchback. And this next topic, you know what? Surprise, surprise. It's called secure transport. Some of you are probably very keen, right? When we're talking about the theory of QoS, we say there are 4 requirements, 4 kinds of user demands. This last one called security, but TCP does not provide security. UDP neither, it does nothing. So hey, if you have an app or service that you want to make sure that the data you're transferring is secure, and so that the user's privacy is ensured, what are the options? Okay, now the first video here is to tell you the older option. It's called S. All right, security TCP. This is the next topic. Yeah, if you recall, when we're talking about these service requirements, right, there are 4 of them. Reliability, which is supported by the TCP. Delay requirement, right, it's somewhat supported by using UDP. Bandwidth requirement, and that might be better supported by UDP, but TCP might do a reasonable job. But the 4th, security. Yeah, the fact is that TCP and UDP, none of them provide security. There's no encryption at all. If we send passwords through the internet straight using TCP or UDP, it's essentially clear text. If there's someone intercepting the message, that someone gets access to our bank accounts or gets into our Amazon.com's account. So none of these cases is good. Big money loss potentially involved. So demand is growing, therefore there is need of these secure layer. So this is secure socket layer. So what it means is that before messages go through the socket and go out on the internet, let's make sure that it's secure. Okay, so it's to provide encryption to messages that's going into a TCP socket. As a result, then we can encrypt messages using a key, or we could verify the receiver using a certificate. Okay. So this is just as important as trying to make sure that the data is confidential. Okay, because how do you know if this server that you are contacting to is indeed a Google server, right? How do you know if it's indeed your bank server? So this is to identify whether the person you're talking to is indeed the person you're expecting. This is just to make sure that no one can understand the message. No third person can understand the message. Okay. And SSL is at application layer. Yeah, it's on top of TCP, therefore it falls in the application layer. But it's also right underneath the application layer protocol, so message go through the application layer protocol, and then to the SSL, and then to TCP. Okay, so this picture below illustrates what I meant here. So SSL right here, right underneath the application layer protocol, but right above the transport layer protocol. Last, SSL socket API. Yeah, to implement SSL, there are APIs available for each programming languages. In chapter A, you will see Python's API to try to encrypt messages before they send messages out onto TCP socket. Now, in this semester, towards the end, one of the PAs, you will also be exercising the APIs in Golang to do secure TCP. But there, we'll be using this, TLS, Transport Layer Security Support. Yeah, this is actually a newer term for SSL. So nowadays, people don't call the security support over TCP SSL. They are all referred to as the TLS, okay? If you think about it, this makes a lot of sense because, hey, SSL there is not really a layer. It's more a support for security, all right? All right, so TLS, the next video, you will learn the exact mechanism. But you see that this video might be a little bit challenging for some of you because it requires knowledge of a certain crypto system called the public key system. Okay, so pay attention. In case you get stuck somewhere, Polly can post the link to the videos about overviewing you guys about the public key crypto. But for now, pay attention. In the video, Polly try to explain what public key is. Okay, just so that in case it's insufficient, Polly will post in the end of the lecture the links to the overview video of public key system. Next, let's explain how TLS works. Before that, let me go back to the very fundamental computer security. How do you encrypt a message such that it can be kept as a secret? So the classic approach is the secret key mechanism. So what we do there is to generate a key, and we share the key with Bob and Alice. So when Alice has a message to send, yeah, use that key K, apply the encryption function, and it's going to generate something that's messy. So a third party in the middle here might intercept the message, but without knowing the key, it's not able to decrypt it. Bob, on the other hand, receiving the messy message, using the key, can restore the original message. Okay, so this is the classic secret key communication. Unfortunately, the secret key system will not work to implement TLS. If you think about it, we have one shared secret key. Let's say if Alice is the one generating the secret key. Alice is yet to send the secret key to Bob, isn't it? I mean, didn't we need TLS because we fear we send password in clear text to the other end? So Alice here is sending the shared secret key in clear text to Bob. Same problem. Yeah, so we do have a bootstrap problem with the secret key. Now, to address that problem, we use this other system on top of secret key. It's called the public key system. So instead of using one shared key, public key system generates a key pair. One is called the private key, the other is called the public key. All right, so the receiver of the secret message is over here. Sender of the secret message is on the other side. What the sender does is to plug the message she wants to send and then encrypt it with the receiver's public key. Yeah, the reason that it's called the public key is exactly because R is going to give out that key to the public, including the sender here. So this is going to scramble the origin. So this function is essentially scrambling the original bits here using this particular parameter. So the encrypted message, as it arrives at the receiver there, then apply the same function and take the received message, and receiver can decrypt with the other key in the key pair. So this is going to give the original message back. Now, the private key is the one kept by the receiver, and no one else in the world will know. Therefore, you ensure that no one else will be able to decrypt the encrypted message. So only the receiver can see the original message. So this is how the public key ensure secret exchange. So TLS illustrated up here works this way. Alice here is a client requesting service from Bob here, a server. So client here first sends hello message to the server. Server in response sends server's public key. So Alice here can then encrypt the shared secret that has been generated before using Bob's public key. So Bob's public key here. Then encrypted master key will arrive at the Bob side. And because Bob is the only one holding the Bob's private key, therefore Bob can restore the master key from EMS. And that's how Bob and Alice establishes the shared secret key. So in this case, you see, Alice is the one generating the secret key. And from then on, all the messages are encrypted using the master secret key. And that's how TLS worked. All right, so public key. And the inventors of the public key system are the Turing winners, because you see how powerful the public key system can be. It ensures a secret transfer of a shared secret that is not supposed to be seen by anyone. Okay, but unless you have a secure channel, how do you do that? And public key system allows you to do that. Now, so the magic is in generating the key pair, the public and private key, such that if you use one to encrypt, you are allowed only to use the other one to decrypt, and vice versa. Okay, so there's a certain way of generating that key pair. All right. All right, and you know what? Perfect time to take a break. It's 11:09, and we'll come back to resume lectures 11:19. Okay, so let's take a break. All right, so welcome back to the second hour of the lecture. Good, so we're just done with section 2.1. So you see, when you're designing an app, you figure out what components, roles, how they connect, and you define the messages you need to send, and you send the messages through a socket. Okay, in that you need to define the port number, you need to define the transport layer service that you want to use to send the messages through. Good. And again, that's the theory. Let's check out a few examples. Okay, and the first one is HTTP. It's the protocol to support this very popular applications that we're using called the World Wide Web. And here's the basic. Now, a couple words before we start playing the video. I understand. Web is the most popular web internet service around the world today. So you guys know very well, okay, how the service is like. But you see, I still need to talk about these basic services and so that I can establish the terminology. Okay, so try to be patient and stay, even though it sounds really simple, because when I transition from the very basic, simple things that you know to things you don't know, you might just miss that transition point. And once you miss that, you will go like, wow, what is Polly talking about? Okay. All right. So a key to make sure that you can learn effectively in college is this: don't underestimate the content. And it's usually a stream. At the beginning, it's easy, and then it will grow complex. So you want to stay patient, even though it's easy, so that you can make the transition smoothly. All right? So bear with the boredom, talking about the obvious things. Sorry. Okay, a misclick on my Stream Deck. Web and HTTP. Let's do a quick review. Web is essentially a bunch of these web pages interconnected. So each web page consists of a number of objects. The base object is typically a HTML file. And then in each file embedded are several referenced objects. And these objects could be another HTML file, could be a JPEG image, could be an applet or a script or an audio file. Each object on the internet, on the web, is addressed by the URL. So this is an example of the URL. There are three parts: the host name, and the path, and the file name. Okay. And the HTTP protocol there to support the web application runs in the client-server model. So the client here are essentially the browsers. The browsers is essentially requesting for web objects and then in turn receiving web objects, of course, using the HTTP protocol. Now, another task the browser does is displaying the web objects. Just to clarify, passing of these messages and web object is the HTTP protocol's job, but displaying web object is actually something else's job. It's the HTML interpreter's job. Yeah, so HTML interpreter is not quite the HTTP protocol. So you see here, a browser, that program there, is a combination of the HTTP protocol client side and an HTML interpreter. So this interpreter is to interpret the HTML page because there are some markups around. Based on the markup, the interpreter will know how to display a web object so that it appears properly and nicely. Now the server, web server, very few of you guys have experience building your web server, I suppose. Yeah, so in this example we see Apache, I think is still the most used server, but this guy here is catching up, and Nginx. Both of these servers are implemented using C and C++ socket. All right. So the web server implements server side of the HTTP protocol. So what it does is to receive requests and send back response. So that's the exact opposite of the client. It's to receive objects and send request. So let's see the exchange. So this client up here, sending HTTP request and then receiving the HTTP response, and containing the HTTP response is the web object. Similarly, if it's a phone, Safari sending HTTP request and server sends back an object, and Safari renders and displays the object. All right, so that's HTTP, Hypertext Transfer Protocol, HTTP. And HTTP runs on top of this transport layer protocol, TCP. And the whole process is actually this. First, tries to establish a TCP connection between the web server and the web client, and then sends the HTTP messages. So before the client and the server sends HTTP messages, the client and the server sends TCP messages first. So starting from the client, initiating a TCP connection. Now, if this is a web server sitting on the default port, it's going to be port 80. And then server would accept the TCP connection, inform the client, and then client can begin sending the HTTP request. And the server sends back HTTP response. When everything is done, the TCP connection will be closed. Know that HTTP, as you see, very simple, request response. In fact, each of these requests is treated as brand new. It's very fresh. That means what the server is doing there is to not record anything about the client. So there's no information about the past client requests. Okay? And we call this type of a service a stateless service. So on the server side, there's no requirement of storing anything about the client. So this is really nice because the server does not require a lot of memory space for these information. All right. Protocols that maintain states can be complex. So this is the other extreme. You might need to maintain the past history, which can be long. And you might need to maintain history for multiple clients. How about that? That's a lot of burden in terms of a memory space requirement. And besides the service load, the memory requirement, what if the server and client each crash while the other continues to run? Then the states on the two sides might be inconsistent, and they will have to resolve the conflict somehow. That's the worst, right? So should you trust the client or should you trust the server? This is one of the classic car problems, all right? All right, so see, the beginning, when Polly was saying, web objects, URLs, you know this very well. And then, right, HTTP works like client sends request, server sends back response. Simple. You might not know exactly this is how it works exactly, but simple. But then, in the end, before HTTP client and server can start sending the request and response, we actually need to initiate the TCP connection first. So the client, before sending the HTTP request, needs to send some TCP messages to the server, and the HTTP server needs to react to that TCP message to first establish a TCP connection. Once that is done, then HTTP request goes to the server. Server there sends HTTP response back. Okay, good. Now, that is the communication model of HTTP, very, very simple. But you see that even as simple as this, someone who implements such an exchange can come up with different modes of speeding up the transfer, okay, for an entire web page. Hey, recall, at the beginning of the video, a web page contains usually a base HTML file. But then inside the base HTML file, it could be sourcing an image file, could be sourcing an audio file. Okay, so there could be additional objects that the page requires to render entirely. Okay, so in a way, these requests is for each of these objects, HTML, as well as each of the objects, the image object or the audio object. Okay, so to get a whole page, you might need to send multiple requests from the browser, right? And so you can think of ways of, collecting these objects, somewhat maybe in parallel or in a way that's more compact. So that is what this video is about. And following the video, quiz 9 is to test you exactly whether you pick up all these different modes of transmitting requests and getting the web object back fast. The video is a little bit long, 8 point something minutes. HTTP connections. There are actually 3 flavors of HTTP connections: non-persistent HTTP, persistent HTTP, and third, persistent HTTP plus pipelining. All right, so let's start from the most basic, the oldest flavor, non-persistent HTTP. This is implemented in the pioneer versions of HTTP, let me call it that way. In that, you send one object per TCP connection. So the clients and the server sets up a TCP connection, and then you send one HTTP request, you get one web object, and then you close the connection right after that. So to download multiple objects, you need to create multiple connections one after another sequentially. Now in persistent HTTP, the main idea is, well, why do we keep opening TCP connections and closing them? Why don't we just reuse the TCP connection we have started in the first place? So in persistent HTTP, client and server establish the TCP connection, and then first web object exchange, second web object request, and the object response exchange, and so on and so forth. So one single connection to send all the objects. All right. Now, the basic persistent HTTP mode works more like that. So you have one exchange to establish TCP connection, and then it's just object 1 and object 2 and then object 3. Okay, but the thing is this: when we establish the TCP connection and sending out the first request for object 1, really before the object 1 is being transmitted back, you see, client over here, it needs only this amount of time to send the request message, right? Client is immediately left idle right after that. So why don't we send the second object's request, the third object's request, and the fourth object's request subsequently and immediately? That way, you just need another exchange like this and just a few more transmission time. Then we're done with everything. Unlike here, for each object, you need this much time, and the second object will wait this much time, and the third object waits even more time. Okay, so this here is the persistent HTTP plus pipelining. Nowadays, when people say persistent HTTP, the implication is that, hey, it's persistent HTTP with pipelining. And by the way, this is HTTP, the 0.9 version. And persistent HTTP without pipelining, that's the HTTP 1.0 version. And the one with the pipelining is the HTTP 1.1 version. All right. Now let's go through the animation for the very standard non-persistent HTTP protocol's behavior. Let's suppose we are looking for this object here. So the URL contains the host name, the path, and the file name. And let's see that this base file here contains 10 reference objects. So there are 10 images embedded. Step number 1, the TCP establishment. Client here initiates connection request. Server sitting at this location at port 80 will accept the connection and then send back a sure, open it message. Second exchange is the client sending the request message. All right, so in the message embedded is the URL. All right, so that's going to go through the socket, and URL right there in the message. Server will receive the message and sees the URL, finds the path, finds the file name, and therefore extracting content and generate the response message. And that response message is shoved again through the socket back to the client. Now, immediately after the response is sent, the server closes the TCP connection. HTTP client here receives the response, parse the HTML file and displays it. And in that process, it's discovered that there are 10 more reference objects to download. And the client then will repeat step 1 to 5 again and again and again, 10 times until all 10 objects are downloaded. And the time to do that is pretty long. Let's try to count the amount of time to complete the entire download. And we call that the time to download an entire page being the response time. Before calculating it, let's define this term. RTT, which stands for round trip time. It is the time for a small packet goes out to the other end and comes back, out and back. So it's a round trip in a sense. So client over here, server code over here, to initiate a TCP connection, the connection request go, connection established, granted messages come, that's 1 round trip time, right? So 1 round trip time for initiating the TCP connection. And it's another round trip time to send HTTP request and receiving the HTTP response. So this part is 1 round trip time. But the dark, thick square here, this is the time it takes to transmit the file. Okay. So when the object is very small, this is very narrow. When the object is large, this could also be quite wide. So let me fill it up. Yeah. So the object itself could be big. The transmission time can be long. So the shadow part is the file transmission time. So the response time to download just one object using non-persistent HTTP is 2 round trip time. 1 here, 2 here, and then the file transmission time. Now we can try to account the response time for that page we were loading, the something.edu, the object there. So we have the base and then 10 more objects. So altogether 11 objects. If we're running the non-persistent HTTP connection, then we have 2 round trip time plus the transmission time for object number 1, the base object. For each of the 10 objects, we do more. Okay, so the transmission time might vary a little bit from object to object, but round trip times remain the same. Right, so there are 10 of these. So 22 round trip time. So 10 of these plus this one over here, the base. And yeah, the sum of the TX. Okay, and depending on which object it is for all I. All right. Now, but for persistent HTTP, the server is going to leave the connection open after sending response. So subsequent HTTP messages between the client and server will be sent over the open connection. Client can send requests, as I said, right? Persistent HTTP without further clarification, it's the persistent HTTP with pipelining. So the client here will send all the 10 requests as soon as possible. Okay. So in the end, it's just 1 round trip time plus the transmission time of all these objects. So altogether, just 2 round trip time. First is to establish the connection. Second is to download the first object. Okay. Third is to download all the rest of the 10 objects. So it should be 3 round trip time plus the transmission time required to send all these objects. So 22 versus 3. Big win over here, right? Yeah. So this is in HTTP version 1.1, the most up-to-date version.
And that takes us to quiz 9. Okay, so that Polly switched to the whiteboard mode. So this is quiz 9. So please tell Polly the response time, okay, of downloading a web page that contains 1 base HTML and 5 reference objects. What that meant is you need to get the first base HTML back to the client first before the client knows the URLs for these 5 reference objects, all right? And for simplicity, let's just ignore the transmission time, all these TXs that might vary a little bit, okay? So Q1 asks, what is the response time? If you send these requests and response through a non-persistent HTTP mode, okay, so that was the original form, isn't it? And what is using the persistent HTTP?
And what is the one using persistent HTTP without pipelining? Because persistent HTTP is by default with pipelining. And so what if we don't have pipelining? Okay, what is the response time? And last one, this one is a little bit tricky. Polly did not mention in the video. What if we could use non-persistent HTTP and start parallel connections to get all these reference objects? So we need to have 2 round-trip time to get the first object, the base HTML. But once we did that, we get the URLs to the 5 reference objects. In the traditional non-persistent HTTP, we actually start the connection to get each of these 5 reference objects one after another. This is saying that, hey, how about we create 5 parallel TCP connections and get all these 5 reference objects back at once? So what will be the response time? Okay, in this case. All right, so this is a relatively straightforward quiz for many of you guys. So you have only 5 minutes. When you're done, come here. Okay, so, to W5 Quiz 9 channel and post your solution there. Okay, you see that Polly also uploaded the quiz problem there. 5 minutes, let's start. So Polly will have to work on it myself as well, non-persistent. Persistent. Alright, so hey, turned out that it might be harder than I thought. Okay. We have the first post from Team 12. Q1, okay, it's also well explained. Nice. 12 round trip time. So 2 round trip time for the base, okay? And then 2 round trip time for each of the reference objects. And for the persistent HTTP, 1 round trip time to establish TCP, 1 round trip time for the base, and 1 round trip time for the 5 reference objects, right? Because pipelined. Okay, so these 5 requests to the reference objects will go out back to back. Q3, 7 RTT. Okay, let's see. 1 round trip to start the TCP connection. 1 round trip to get the HTML file, the base, right? Because you need to get the base first before you know the URLs of the 5 reference objects. Good. But once after that, persistent HTTP is to keep the TCP connection. Therefore, these 5 requests, although we don't do it pipelined, but one can get one of these reference objects in 1 round trip time. Okay, next. And one after another. So 1 round trip time per object, and 5 objects, 5 round trip time. So 1 round trip, 1 round trip, and 5 round trip. Oops. 7 RTT. So far, so good. I guess what's tricky for you guys is Q4, right? Because Polly did not talk about this mode of connection. So obviously, we need to establish a TCP connection. And of course, 1 round trip to get the base HTML. But this is non-persistent connection, so we close this TCP connection. But the browser at this point knows that there are 5 more reference objects I need to get. In each, we will need 1 round trip time to start a TCP connection, and then HTTP request response to get the object, and close the TCP connection, right? So this is the characteristic of the non-persistent HTTP. You start a TCP connection and you use it to get just 1 object, okay? Whether it's the base or the reference object, okay? But the thing is this, for these 5 objects, you can start 5 parallel connections. So, hey, 5 parallel connections, 2 round trip time to get 5 objects in at once. Okay, so 2 round trip times for the reference objects, 2 round trip times for the base object, together 4 RTT. All right. Okay, so I mean, oops. Yeah, the answer looks good to me. And Min Luan is the first. Okay, great. Let's see, Brian. For team 10, 2 round trip time for 1 object. Yeah, and there are 6 objects in total, right? So 12. 1 to initiate, 1 for the base, and 1 for the 5 reference objects in pipeline. 5 for 5 reference objects, each 1 round trip, but not pipelined. Very good, very clear description. 2 for the first base, and 2 for the 5 reference. So again, 4 round trip time. Very good. Okay, I think yeah, once the first one is brave enough to post the first solution, then you guys follow suit. 12, 3, 7, 4. Yeah. Okay, so make sure that you explain how you come up with the numbers, because it's very easy that you just, take the numbers. The trouble is that when you're doing an exam, not knowing exactly how it works, you will then have trouble answering question there. All right, great. So yeah, I think you guys get it now. And we'll move on. Okay, sorry, some of you guys are still typing. Feel free to stay here for a little bit of time. And we move on to talk about the message. Okay, now we know the architecture and how they connect. Let's talk about the messages defined for the HTTP protocol. There are 2 types of messages we send, and you hear Polly saying it again and again: the request and the response. Okay, so that will be topic A and topic 10. So quiz number 10 will follow immediately after this video that talks about request message. Oh, by the way, this video I meant 3 parts. Okay, a video in 3 parts. So let me give you an example of the request message first. HTTP connections. There are actually 3 flavors of HTTP. Sorry. Another misclick of Stream Deck. I meant this. Let's take a closer look at the syntax of HTTP request message. First is the request line. It's only a single line, 3 tokens, separated by 2 spaces. 1 over here and 1 over here. First token indicates the command the client is issuing to the server. So get here is the most classic command. Second token here indicates which object the client is wishing to download. So here you see the path and the file name of the object. Third token is very straightforward. It's simply telling the server the version of the HTTP protocol the client is implementing. Now, header lines. Syntax is also quite straightforward. Column in the middle. Before the column, this is called the attribute or the field name. And whatever comes after the column is the value of the attribute or the value of the field name. All right, so user agent is a well-defined attribute in HTTP. It indicates what implementation the browser is and the version of it. So user agent indicating the meaning being user is using a browsing agent called Firefox, and it's version 3.6.10 of Firefox. Okay, similarly, keep alive, also a predefined attribute. And the value 115 is saying that let's keep the connection alive for 115 seconds if there are no messages being sent. Connection indicates the type of connection the client is wishing to establish. It's the keep alive kind of connection. And so you see the syntax and a little bit of semantics of HTTP requests. All right, so you see from the example roughly already, right, there are 3 parts in a request message: the command, and then the header lines, and then the rest, the content. Okay, but in request message, usually the content is empty. Now, what's a little bit tricky is the header line. You see very often there's a field, and then the value for that field. Okay, so sometimes we call these fields also attributes. Attribute and the value of the attribute. Okay, and no worry, this video is to talk more generally and formally about the request message format. Next, the general format. Okay, now with that introduction, with a specific example of HTTP request, so this will be slightly easier. You see here, first is the request line. And then we get a whole bunch of these header lines, and it ends with what? CRLF. Okay, in fact, at the end of every line, CRLF, CRLF. Okay. And in the request line, we have three components: the method, the argument for the method, and the version. Okay. Some comments might not contain the second component. All right. And you see here, for each header line, we see what? Pair of attribute name and value. So in the slide, we see this is the header field name. So those attributes are sometimes also called the fields, the field names. So attribute value, or field name value. Good. So lots of these. Okay. And hey, this is the thing that we did not see in the previous example. Yeah. Occasionally, you do need to have a body in the HTTP request message. And this is what, if you recall, the post comment. We're sometimes posting content, posting data onto the server. So those data, those information to be communicated from the client and to be registered at the server will be here in the entity body. So real data generated by the user is here. Okay. So officially, in general form, the HTTP request comes in three parts: request line, header lines, and body. But for most of the HTTP requests, there's just two parts: the request line and the header lines. Now, let me add a little bit more. First, the post method. You've heard me. There are sometimes web pages that you need to fill forms, okay? Input names, usernames, potential passwords. Okay, those input are uploaded to the server in the entity body. There's another way of doing that recently. Okay, it's called the URL method instead of the post method. What you do there is, hey, you could be clicking just buttons, okay, a certain link, in fact. What the browser does there behind the scene is more like this, okay? Requesting to the server, all right, okay, but it's actually sending a phrase like this. Instead of a file name with a path, okay, so instead of having a path, something, and then something.html, so it's a very weird form of HTTP request, okay? While we know this is more classical, but these days we see this more. Animal search, question mark, and then something and something. Okay. So this is actually a query. Okay. Unlike request sounds more like requesting for a service, requesting for a file, for an object. But clients often query the server for a service. Okay. For example, look up a database. Exactly. So in a way, the World Wide Web is evolving from a huge hard disk, a global distributed hard disk, to a global distributed database. Okay, so in the HTTP request there, we are actually sending a query. This is the name of the query, and this is the input to the query. So this query obviously contains two arguments in order to execute, for the server to execute. All right. It's using the get method instead of the post method earlier. So this type of a service request is using the get method, but in HTTP request message. And the input is exactly in the URL field in the request line. Okay, and it's this way. Yeah, the query name and then the arguments for the query. Right. All right, so that's request message formats. So in terms of methods, there's downloading methods, there are uploading methods as well, and you're just seeing two examples. All right, good. And this is the last quiz this week. In fact, after this is done, you're free to go. So this is quiz number 10, one of the easiest quiz you've ever seen in this course. Okay. So what I'm showing here in the box is an HTTP request message. So one can actually intercept such a message using tools like WinDump. Okay. You can also use a a Chrome developer tool to get this. Okay, the exact HTTP request messages being sent from your browser to the server. Okay, so this is the content. Now, I ask you to read this content here, okay, this HTTP request message, and tell me, this is a HTTP request message, and what is the document it is requesting? And what is the URL of that document? And where do you see that? Okay, where do you see the URL of the document being requested? And Q2, is this request sent through a persistent or non-persistent connection? Okay, and how do you tell whether this is a request through either persistent or non-persistent connection? All right, so very simple quiz. You have 3 minutes to think about. When you're ready to post, come to channel W4, quiz 10. Okay, and Polly, start counting time. 3 minutes. Yeah, so it seems quite obvious, right? The URL is CS453 and the machine, okay, it's actually trying to connect to is gaia.csumass.edu. All right, and and you see also that in the command line, it's HTTP 1.1, therefore it's persistent connection mode. All right, but Team 1 says here, accepting objects after opening connection. I guess it's probably because at the very last header line, connection column keep alive. So the connection is kept alive after, okay, the request being served. There. Yeah. Keep alive. Interesting. That people try to determine whether this request is going through the persistent connection mode or not, looking at different parts, okay, in the request message. Keep alive. Oh, this is the full answer, right? You have two places you can see that this is going through the persistent connection. Yeah, so you have the host and you have the URL. Very good. You guys have got it. And that is the HTTP request message, okay, and the format. Bottom line, it's readable message, okay. So when you intercept it with tools, you can see exactly what's in there. All right, so that's actually all the time we have for the videos today. But I do owe Glady an answer for his question about stateless. So we talk about UDP being stateless because it's not tracking anything. So the receiver of a UDP connection is not tracking anything about the sender. So it's not doing recovery, nothing. So UDP in this sense is also stateless. Okay. So think of stateless as simply a subjective, okay, describing in UDP receiver do not record anything about the sender. HTTP at a higher level, the receiver side of the HTTP messages, so it can be client and server, both of them stateless of the other end. So HTTP request receiver does not record anything about the sender of the request. HTTP response receiver does not record anything about the sender of the response. Okay, but you know what, Glady? This was actually what HTTP was designed for in the first place. But later on, there are additional mechanisms people add to web browsing so that they can track the state of the other end a little bit better. And there's a reason for that. Okay, that's in fact what we will be talking about next week. It's called cookie. So hey, as a web user, a lot of times we want to know, we want to be a little bit convenient when we access the same server that we go to very often. That way we don't need to keep logging in again and again. So if HTTP is stateless, how can you stay on and use a particular service without logging in after you close your connection, go out and do something and come back to try to connect again? So cookie, making HTTP somewhat stateful is convenient for the user. It's also convenient for the service provider because then they can actually analyze their users a little bit. Okay, getting to know what the users prefer, okay, buying. So they can recommend products that are probably looked after by the users. Okay, so cookie coming up next week. And with that said, it's perfect timing to close the lecture today. So Polly will come back to your quiz answers after the live stream stops. So come again next week. Okay, I'll see you then. Bye. And the music, I guess you're waiting for that. Bye. 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 Oh. Oh, sure. Okay, bye. Okay, so let me end the stream.